Hi, in this video we want to develop some formulas for angular velocity and angular acceleration. This video roughly relates to Young and Friedman's University Physics Chapter 9 Section 2. What are formulas for angular velocity and for angular distance and so forth, assuming a constant acceleration? Now, you might remember back in Chapter 2 of Young and Friedman's University Physics, or no matter what physics book you're talking about, you're going to get into the various equations for the relationships between velocity and distance and so forth. You're going to get into those very early on in any physics book. Usually by Chapter 2, you're into those formulas for velocity. Do you remember these? So these are the formulas for straight line movement. So velocity 2, your ending velocity. Let's say you're on a straight road. There are no hills, no bumps, no curves. It's just a straight road, straight line motion. Let's say you start at velocity 1 and you go down that road for a particular amount of time at a constant acceleration. Well, what velocity are you going to be at after time t? Well, it's going to be your initial velocity, v1, plus that constant acceleration times the amount of time you're on that road. And that's going to give you v2, your closing velocity. These are, again, equations that I hope are very familiar to you if you're in a chapter on angular rotation and acceleration. Hopefully you remember these formulas from the very beginning of your physics book. So let's say you're on that straight line at a constant acceleration. You can know how far you've gone on that road if you know where you were on the road when you started, x1, the initial velocity, v1, the amount of time you've been on the road, and if you know the constant acceleration. That's the second formula, and so forth. Now what we're going to find is that the formulas for angular velocity and angular acceleration are going to be pretty much exactly the same. And again, if you want to see derivations, I'm sure your physics book is going to show you that. And so if you have a wheel or a propeller, or you have a pulley or any kind of a circle that is undergoing a constant acceleration, then you're going to be able to tell what the angular velocity is after a certain amount of time. That's omega 2. If you know what velocity it was at, or what angular velocity it was at when it started, omega 1, plus the constant acceleration times the amount of time that is elapsed. So omega 2 equals omega 1 plus at. This is, again, very, very much the same as the formulas that we had for velocity and so forth in Chapter 2, in the chapter on straight line motion. Now, one important thing to say, this relates to the next section in this chapter, is that the angular velocity here is in radians. It's not in meters or any kind of distance. It's in radians. So the next chapter will tell you how to convert, as it were, radians per second into meters per second and so forth. That's yet to come. These formulas are just for velocity in terms of radians, say radians per second for the velocity. Very important. Watch the next video on correlating velocity with in other measurements with radian velocity. Okay, so we take the distance formula here. If theta is the angle in radians, so that's kind of like the distance, because in radians theta is how far you've gone, as it were, around the circle. So theta 2, that is the total circular distance you've gone, is equal to theta 1, where you started on that circle, plus omega 1t, which is, again, the initial angular velocity times the amount of time elapsed, plus 1/2 that constant acceleration time squared. Again, this is exactly the same formula. By the way, I have my equation, the x equation needs a t after the a, but you get the picture. Two more formulas. So here's another formula from Chapter 2. Distance 2 minus distance 1 equals the average velocity times t. So same thing. Theta 2, the distance around it ends up, minus theta 1, the angular distance from where it started, equals the initial angular velocity, the final velocity, angular velocity, added together divided by 2, that's the average angular velocity, times the time that has elapsed. One more equation. This is always the hardest one for me to remember from Chapter 2. So the final velocity in straight line motion, the final velocity squared equals the initial velocity squared plus twice that constant acceleration times the difference in distance covered. Notice that this particular equation has no time in it, so it's useful when you don't know the time to be able to get at these things. Well, in angular velocity, exactly the same. So the closing angular velocity squared equals the initial angular velocity squared plus twice that constant acceleration times the difference in distance between where it ends up, theta 2, and where it started, theta 1. So those are the formulas for angular velocity and acceleration, and they are exactly analogous to the formulas for straight line velocity and acceleration.